A uniform disk of radius 0.12 meter and mass 5 kilogram is pivoted such that it rotates freely about its axis. A string wrapped around the disk is pulled with a force of 20 Newton. What is the torque exerted on the disk? What is the angular acceleration of the disk? If the disk starts from rest, what is the angular velocity after 3 seconds? What is the kinetic energy after 3 seconds? What is the angular momentum after 3 seconds? Find the total angle the disk turns in that 3 seconds. And finally, show that the work done by the torque equal to its kinetic energy. All these are one-step problems actually. Just use the principles we discussed so far. So none of these is involved more than a single step. Okay, let's go. First of all, we have a disk of radius 0.1 meter and mass 5.1 kilogram, pivoted so that it can rotate about a horizontal axis. Alright. Now, we got the mass of the disk is 0.5 kilogram, the radius of the disk is 0.12 meter, a tangential force of F equal to 20 Newton is applied on the disk. This is the first thing. What is the torque exerted on the... Well, I just showed it to you earlier that if you have a disk like this and if you apply a tangential force, the torque of that tangential force will be, what will be the torque? It will be the force multiplied by the radius of the disk. Alright, so as I said, it's a single step problem. Now, F equal to 20 Newton is tangential to the disk, that is perpendicular to the radius. Therefore, torque tau equal to radius multiplied by that force, and that will be 0.12 meter times 20 Newton, that is 2.4 meter Newton is the torque produced by that force. Well, once you know the torque, you can find the angular acceleration. Well, in order to do the angular acceleration, we need another quantity. What is that? We need the moment of inertia. Alright, the moment of inertia of a disk is 1/2 mr squared. So that will be 1/2 times 5 kilogram. I wrote m equal to 0.5 kilogram. Yeah, it has to be 5 kilogram. So that will be 1/2 times 5 kilogram times r squared 0.12 squared. That is 0.036 kilogram meter squared. So we now know the torque, 2.4 meter Newton. We know the moment of inertia. Therefore, we can find the angular acceleration of the disk. Tau equal to I alpha. Therefore, alpha equal to tau over I. That will be 2.4 meter Newton divided by 0.036 kilogram meter squared. That is 66.7 radian per second squared. Okay, so we have done part B. What's part C? If the disk starts from rest, what does that mean? Omega 0 equal to 0. What is the angular velocity after 3 seconds? Well, simple use of the formula. Omega F equal to omega 0 plus alpha t. Where we have this alpha, we will carry this alpha value with us. So omega 0 we know is 0. Alpha we just calculated. Time is 3 seconds. we need to find omega F. Omega F equal to omega 0 plus alpha T. That will be 66.7 radian per second squared times 3 seconds. That is 200 radian per second. Alright, now what is D? We need to find the kinetic energy. What is the kinetic energy? Kinetic energy of rotation is 1/2 I omega F squared. Well, we know I, we just calculated I earlier. We know omega F we just calculated. Therefore, kinetic energy of rotation is 1/2 times I is 0.036 kilogram meter squared times omega squared is 200 radian per second squared, and that is 720 joules is the kinetic energy after 3 seconds. What is E? Angular momentum. What is the angular momentum at that time? Angular momentum equal to I omega. Again, we know I, 0.036 kilogram meter squared. We know omega, we have the omega value. Therefore, angular momentum is 0.036 kilogram meter squared times 200 radian per second. That is 7.2 kilogram meter squared per second. Now, what is the total angular displacement during this time, during these 3 seconds? We know that the theta 0 is 0, we say starting from 0. Omega 0 is 0, is that right, starting from rest. Alpha is 66.7 radian per second squared. T equal to 3 seconds. We need to find theta, the angular displacement. Which of the equations will you use? Theta equal to theta 0 plus omega 0 t plus 1/2 alpha t squared. There you are. Where theta 0 is 0, omega 0 is 0, so the first two terms will go. That will be 1/2 alpha, 66.7 radian per second squared, times t squared, 3 seconds all squared. And that is 300 radian is the angle it described during that time. Suppose I ask you, how many revolutions did it complete during that time? How do you do that? 300 radians is how many revolutions? Each revolution is 2 pi radians. Therefore, 300 radian will be 300 divided by 2 pi revolutions. Alright, what's the next thing that we need to find? In G, we need to find the work done. The work done in rotation is tau times the angular displacement. Tau theta. Tau we know is 2.4 meter Newton. Theta we just calculated 300 radians. Therefore, work done, rotational work done is tau times theta, 2.4 meter Newton times 300 radian. That is 720 joules. Do you remember the kinetic energy we calculated? What is the kinetic energy amount we calculated? 1/2 I omega squared is 720 joules. Look at this. Kinetic energy is a measure of the work done to give the object a particular angular velocity. So the work done is a measure of its kinetic energy. Suppose I ask you, what is the amount of work that now needs to be done to bring this disk to stop? The amount of work that needs to be done to bring it to a stop will be negative 720 joules. Alright? Okay. Another problem. What is the angular momentum of a 2-gram particle moving in a horizontal circle of radius 15 centimeter with an angular speed of 6 pi radian per second? Angular momentum is mv times r. Well, we have the mass as 2 times 10 to the negative 3 kilogram, 2 gram. R, the radius is 0.15 meter and omega is 6 pi radian per second. I equal to mr squared, is that right? The moment of inertia of a particle of mass m at a distance r from the axis of rotation is I equal to mr squared. So in this case, the mass is 2 kilogram, the radius of the disk is 0.15 meter, and therefore the moment of inertia of this particle about the axis of rotation is 4.5 times 10 to the negative 5 kilogram meter squared. Well, if you know the moment of inertia and the angular velocity, can you calculate the angular momentum? L equal to I omega. And we just calculated I, we know omega, therefore angular momentum is 4.5 times 10 to the negative 5 kilogram meter squared times 6 pi radian per second, and that is 8.5 times 10 to the negative 4 kilogram meter squared per second. Let's do one more problem. A skater has a moment of inertia 100 kilogram meter squared when his arms are outstretched, and a moment of inertia of 75 kilogram meter squared when his arms are stuck close to his chest. If he starts to spin at an angular speed of 2 revolutions per second with his arms outstretched, what will his angular speed be when they are tucked in? You can see this is a question using the conservation of angular momentum. Is that right? I1 omega 1 equal to I2 omega 2. Alright, I1 is 100 kilogram per meter squared and I2 equal to 75 kilogram meter squared. I1 is the moment of inertia when his arms are outstretched. I2 is the moment of inertia when the arms are tucked in. Now, what is the angular velocity? What is the angular velocity initially when the arms are outstretched? It is 2 revolutions per second. You can leave it in that unit. If you leave omega 1 in revolutions per second, omega 2 will also be in revolutions per second. Or you can convert it as radian per second. 2 times 2 pi radian per second. Is that right? Revolutions per second is multiplied by 2 pi to make it radian per second. Since the angular momentum is conserved, we have I1 omega 1 equal to I2 omega 2. And therefore omega 2 equal to I1 omega 1 divided by I2. And that will be I1 we know, omega 1 we know, and I2 we know. And that will be 16.8 radian per second will be, and that's the reason why the skater will now go faster. It's almost, is that right, much bigger than the earlier angular velocity. Well, we have now done a spectrum of different types of problems, and you must be able to do now any basic 1 or 2 step problems using the concepts of rotation. Alright, I'm going to stop this lesson here. I will take you to the next lesson, which is conditions of equilibrium of an object.